To get started with PyCharm, visit the JetBrains website. Choose the version that's right for you, the free community edition or the paid professional edition. Select your operating system, download the installer, and run it. Follow the installation prompts, and you'll have PyCharm set up in just a few steps. On the Windows operating system, you'll see a few optional settings during installation. First, there's the option to update the path variable. This allows you to run Python and PyCharm commands directly from the command line, recommended if you want easy access. Next, there's Open Folder as Project, which adds a right-click option to open folders in PyCharm straight from your File Explorer, which is a useful shortcut for quick access. And finally, there's the option to create associations for .py files, making PyCharm the default program for opening Python files. Once the installation is complete, open PyCharm for the first time. Accept the terms of use, and then choose whether you'd like to share anonymous usage data. To create a new project, open PyCharm and click on New Project. Choose a location, give your project a name, and then select your Python interpreter. You can stick with the default interpreter or choose an existing virtual environment if you have one set up. This process might take a moment depending on your computer. If you're on Windows, you may see a pop-up about Windows Defender. Click Automatically and then accept the security prompt to give PyCharm the necessary permissions. This will allow it to add an exception for your project folder in Windows Defender. You'll notice at the bottom of the PyCharm window that it's still setting things up. Just wait until it finishes installing everything. Eventually, you'll see another pop-up indicating that the project folder has been successfully added to the Windows Defender exclusion list. Once PyCharm is finished, the progress bar at the bottom will disappear, signaling that you're ready to start working on your project. In the PyCharm window, you'll notice a File Explorer on the left side displaying your project files. We can collapse the V&V folder, which contains the virtual environment that PyCharm created for our project. If I click on this icon once, the menu expands. From there, I can select File and then click New. Here I can click on Python file. I'll name it main and press Enter on my keyboard. That creates a main.py file in our project folder. To test it, I'll write a simple print statement. To run my Python project, I can right-click on the main.py file and select Run. This automatically opens the output window, where we can see the result of our print statement. Now let's add 2 more print statements so we can demonstrate a few more features of PyCharm. First, we can also run the program using this button here. Just keep in mind that this will run the currently selected file, so we need to have the main file selected. That's not an issue right now since we only have one file. Our program ran successfully, and we can see all 3 print statements in the output window. Now, I did this so we can see how to step through our code using debug mode. This area next to the lines of code is called the gutter. By clicking on a line, we can add a breakpoint, which is shown as a red circle. This means that when we run the program in debug mode, execution will pause at that line. To run the selected file in debug mode, we can click this icon next to the run icon. After a moment, the line with our breakpoint turns blue, indicating it's about to be executed. Note that it hasn't run yet. The program has paused right before executing this line. We can confirm this by selecting the console window to view the program output, where we can see that our first print statement hasn't been executed yet. Down here, there are a few buttons that are useful for debugging. These buttons allow us to step through our program line by line. The main buttons we'll use are Step Over and Step Into. Step Over moves to the next line without entering functions, while Step Into goes into the functions so we can see their execution in detail. If we click Step Over once, 2 things happen. First, the output of our print statement appears in the console window, indicating that our first line executed successfully. Second, the blue highlight moves to the next line, showing that the next line to be executed is now the second one. Notice that the program is still paused, waiting to execute this next line. This lets us execute our program line by line, no matter how complex it is. That's essential because we often introduce mistakes in our code that can only be found and fixed by stepping through it line by line. That's actually where the term debugging comes from. It means finding and fixing bugs in our program. To wrap up, I can press the Step Over button a couple more times to continue seeing the execution of the program line by line. Syntax is essentially a set of rules that defines how code should be written, like a language's grammar. In Python, the syntax is designed to be clean and easy to read, making it beginner-friendly. Each line of code is executed in sequence, running from top to bottom. This structure helps make Python code both logical and straightforward. Unlike other languages that use symbols to separate code blocks, Python uses indentation, meaning spaces or tabs at the start of a line. For example, when we write a condition, the lines within that condition are indented, letting Python know they belong together. This indentation makes the structure of the code clear and easy to follow. Comments are notes added to the code that Python ignores when the program runs. They start with a special symbol and are mainly used to explain what the code does. Adding comments can be really helpful, both for others reading your code and as reminders for yourself. The print function is used to display text or numbers on the screen. It's a simple way to show information, whether it's a message, a result, or any other output you want the user to see. Think of variables as containers that hold data values like names or numbers. You assign a value to a variable using an equals sign, which stores the data so you can use it later in your code. These are the basic data types you'll work with in your code. A string is used for text, like a name or any other words. An integer is a whole number, useful for counting or indexing. And a float represents decimal numbers, which come in handy for more precise values like measurements. A variable name must start with a letter or an underscore. You can also use numbers within the name but not at the start. Also, be careful not to use Python keywords as variable names, as that is not allowed. Just like text, Python can store numbers in variables, allowing you to work with numerical data easily. The main types of numbers you'll encounter are integers, which are whole numbers, and floats, which represent decimal numbers. Python has math operators to work with numerical variables. For addition, you simply use the plus symbol, and for subtraction, you use the minus symbol. When you want to multiply, you can use the asterisk, and for division, you can use the /. One thing to note is that division always returns a float, even if you're dividing two whole numbers. This means that even when the result is a whole number, Python will still give you a decimal value. Floats are great for handling those decimal results, giving you more precise calculations. Floor division gives you the whole number part of the division, ignoring the decimal. In other words, it rounds down to the nearest integer. So when you divide 7 by 3 using floor division, the result is just the whole number, which is 2. The modulus gives you the remainder after dividing two numbers. So if you divide 7 by 3, the modulus will give you the remainder, which is 1. This is useful when you need to know what's left after division. Exponentiation is used to raise a number to a certain power. For example, when you raise 2 to the power of 3, the result is 8. This is a common operation for calculations involving powers and scaling. You can use multiple operators together to create more complex calculations. Python follows the standard rules of math to determine the order of operations. This means multiplication happens before addition. So, in the example of adding 2 to the result of 3 multiplied by 4, Python first multiplies 3 and 4, then adds 2 to get the final result of 14. Strings are used to store text in variables, and they're always enclosed in quotes. You can use either single quotes or double quotes to define a string, so both are perfectly fine. The plus operator is used to join two strings together, a process known as concatenation. However, keep in mind that spaces are not added automatically. So if you want a space between the strings, you'll need to add it explicitly. For example, when combining a first name and last name, you can add a space between them to get the full name. We also have the repetition operator in Python. This operator allows you to repeat a string multiple times. It's a simple way to create repeated patterns in your code. A function is a reusable block of code designed to perform a specific task. By grouping code into functions, you can keep your programs organized and easier to read. Functions allow you to avoid repeating code, making your programs more efficient and manageable. To declare a function in Python, you use the def keyword followed by the function name and parentheses. The code block for the function, where you define its behavior, is indented underneath. Once you've declared a function, you can run the code inside it by calling the function. To do this, simply use the function name followed by parentheses. This tells Python to execute the code defined inside the function. Functions can also accept inputs, called parameters, which allow you to customize their behavior. Parameters are placed inside the parentheses after the function name. By passing different values to these parameters, you can make your function perform various tasks without rewriting the code. When you call a function that has parameters, you need to pass values to those parameters. These values are called arguments. By providing different arguments, you can customize how the function behaves each time it's called. Functions can also return a value using the return keyword. When Python encounters a return statement, it ends the function and sends the result back to where the function was called. This allows you to store the returned value in a variable or use it for further calculations. Python comes with many built-in functions to handle common math tasks, so you don't need to import any extra libraries. The abs function is used to get the absolute value of a number. It removes any negative sign, so no matter what number you pass to it, you'll always get a positive result. The pow function raises a number, x to the power of y. It's equivalent to using the exponentiation operator. The max function helps you find the largest value in a set of numbers, while min finds the smallest. These functions are useful when you need to quickly identify extremes in a group of values. The round function is used to round a number to the nearest integer. You can also specify the number of decimal places you want by adding a second argument. Python provides built-in functions that make it easy to work with strings. These functions allow us to modify, analyze, and manipulate text data, making tasks like searching, changing case, or trimming spaces much simpler. The len function returns the number of characters in a string. It's useful when you need to know the length of a piece of text. The lower function converts all the letters in a string to lowercase, while upper does the opposite, converting all letters to uppercase. These functions are useful when you want to standardize the case of your text. The strip function removes any spaces or extra white space at the beginning and end of a string. It's helpful when you want to clean up user input or text data. The replace function allows you to replace part of a string with another string. You provide the part you want to replace and the new string you want to use. You can use the in keyword to check if a substring exists within a string. It returns true if the substring is found and false if it's not. A Boolean can hold only one of two possible values, true or false. These values are often used to represent simple yes or no conditions or on and off states. Comparison operators help us compare values and return Boolean results, either true or false. Some of the most common comparison operators are double equals for checking if two values are equal, not equal for checking if two values are different, and greater than or less than signs for comparing size. Boolean logic allows us to combine or modify conditions using the keywords and, or, and not. With and, both conditions must be true for the result to be true. With or, only one of the conditions needs to be true for the result to be true. And finally, not simply reverses a Boolean value. If something is true, not makes it false, and vice versa. Conditionals allow us to make decisions within our code. They enable us to run specific blocks of code only when certain conditions are met, making our programs responsive to different scenarios. For instance, with conditionals, we could check if it's sunny and decide to wear sunglasses, or if it's raining, we could bring an umbrella. This ability to control the flow of code based on conditions is fundamental for creating dynamic and interactive programs. The if statement is used to check a specific condition. If the condition evaluates to true, the code block that's indented beneath it will run. The else statement is used as a fallback for if statements. When the condition in the if statement is false, the code block under else will run, allowing us to define an alternative action. The elif, or else if statement, allows us to check additional conditions if the previous if or elif conditions are false. You can chain multiple elif statements to evaluate several conditions in sequence. Nested conditionals allow you to place if statements within other if statements. This lets us check additional conditions only if the outer condition is true. While nesting can be useful, it's important to use it sparingly, as too much nesting can make code difficult to read. String comparison operators let us compare two strings to see if they match or differ. Just like with numbers, the result of a string comparison is always a Boolean value, either true or false. Just like with numbers, we can use common comparison operators to compare strings. The most used ones are double equals for checking if two strings are equal, not equals for checking if they are different, and greater than and less than for comparing which string is greater or less in lexicographical order. String comparisons are case sensitive, which means that capitalized apple and all lowercase apple are considered different strings. A loop is a programming structure that allows us to repeat a block of code multiple times. This is especially useful for tasks that involve repetition, as it eliminates the need to write the same code over and over. In Python, there are two main types of loops, the for loop and the while loop. Both help us automate repetitive tasks and streamline our code. The for loop is used to iterate over a sequence, such as a list, tuple, or string, or even a range of numbers. It allows you to repeat a block of code for each item in the sequence. In this example, we used the range function with 5 as argument, which generates numbers from 0 to 4. The loop iterates over each number in the range, and for each iteration it prints the current number. The while loop runs as long as a specified condition is true. It keeps repeating the block of code inside the loop until the condition becomes false. In this case, we start with a variable count set to 0. The loop will continue running as long as count is less than 5. On each iteration, it prints the current value of count, and then we increment count by 1. Sometimes, we need more control over how a loop behaves. Python provides two useful keywords, break and continue. The break statement exits the loop prematurely when a specific condition is met, stopping further iterations. The continue statement skips the current iteration and jumps directly to the next one, without executing the remaining code in that cycle. A nested loop is simply a loop inside another loop. The inner loop runs completely for each iteration of the outer loop. This allows us to handle more complex repetition, like when we need to iterate over multiple dimensions or multiple sets of data. Imports in Python let you bring in code from other files, known as modules, or from external libraries, to use directly in your program. This approach promotes code reuse and makes it easier to keep your code modular. Python offers an extensive standard library packed with useful tools, and you can also tap into a wide range of third-party libraries to expand your project's capabilities. To use a module in Python, you'll need to import it with the import statement. The general syntax is simple. Just write import followed by the module name. Here's an example of importing a module. We're using Python's built-in math module, which provides access to various mathematical functions. You can also import specific functions from a module instead of the entire module, which can make your code more efficient and reduce memory usage. The syntax is straightforward. Use from, followed by the module name, then import, and the specific function name you need. In this example, we're importing the square root function directly from the math module, rather than importing the entire module. This allows us to call square root directly. This approach is efficient when you only need specific functions from a module. You can assign an alias to a module or function using the as keyword. This is especially useful for making your code more concise or avoiding naming conflicts. You can import multiple functions from a module at once by separating them with commas. In this example, we import both square root and pow from the math module. You can import all functions from a module at once by using an asterisk. However, this approach is generally not recommended because it can lead to naming conflicts if different modules have functions with the same names. You can create your own module by saving Python functions in a separate .py file. Once saved, you can import it into other files just like any other module. Lexical scope, also known as static scope, refers to the visibility and lifetime of variables based on where they are defined in your code. In simple terms, a variable is accessible within the block of code where it's defined, including any nested blocks inside that scope. Variables in Python can have either global or local scope. Global scope means that a variable is defined outside of any function or block, making it accessible anywhere in the module. On the other hand, local scope refers to variables defined inside a function, which are only accessible within that function. In this example, we have a global variable x defined outside of any function, and a local variable y inside the myFunction function. When we call the function, both x and y are accessible within it. However, outside the function, only the global variable x is accessible. If we try to print y outside the function, it would raise a name error since y is only available within the function's local scope. An inner function can access variables from its outer function. In this example, the inner function can access the variable outer var defined in outer function. The non-local keyword allows you to modify variables in an enclosing scope, but not the global scope. It's especially useful in nested functions when you want to change a variable from the outer function. In this example, non-local count inside inner function allows us to modify the count variable defined in outer function. Each time we call inner function, it increments count and prints the updated value. The global keyword lets you modify a global variable inside a function. Without it, Python would create a local variable instead of using the global one. Data structures are ways of organizing and storing data to make it easy to access and manipulate. Python offers several built-in data structures that are designed to handle different types of tasks efficiently, allowing you to choose the best one for your needs. Lists are ordered and mutable collections of items. Tuples are similar but immutable, meaning their content can't be changed. Dictionaries store key-value pairs in an unordered fashion, allowing fast lookups by key. Finally, sets are unordered collections that only store unique items, making them ideal for removing duplicates. Lists in Python are ordered collections that can store items of various data types. You create a list using square brackets. A list can contain any values, and its elements can be accessed by their position or index. Lists are also mutable, meaning you can add or remove items after the list is created. There's a link on the slide for more detailed information if you'd like to dive deeper. Tuples are similar to lists, but with one key difference. They are immutable, meaning once you create a tuple, you cannot change its elements. You define a tuple using parentheses instead of square brackets, and you can access its elements by their index, just like with lists. However, since tuples are immutable, you can't modify them after they are created. For more detailed information, there's a link on the slide that takes you to the official Python documentation. Dictionaries in Python store data as key-value pairs. Each key in a dictionary must be unique, and you use the key to access its associated value. You define a dictionary using curly braces. A dictionary can store information like a person's name and age. Dictionaries are useful when we need to access data quickly. Since they store key-value pairs, we can directly access specific values by using the keys. Sets in Python are unordered collections of unique items. They are especially useful when you need to eliminate duplicates or test for membership. You can define a set using curly braces or the set function. If you add an item that already exists in the set, it will be ignored, ensuring that the set only contains unique elements. Type conversion, also known as typecasting, is the process of changing one data type into another. In Python, this can happen in two ways: explicitly, where you manually convert the type, or implicitly, where Python automatically converts it for you when needed. Type conversion is important for several reasons. First, it ensures compatibility between different data types and expressions. Second, it helps prepare data for functions that require specific types. Lastly, type conversion is crucial when handling user input, as it allows you to perform calculations with the correct data type. Implicit type conversion happens automatically when Python needs to perform operations involving different data types. For example, if you add an integer and a float, Python will automatically convert the integer to a float before performing the operation. Explicit type conversion is when you manually convert one data type to another using built-in functions. For example, you can use int as a function to convert a value to an integer, float to convert it to a float, or str to convert it to a string. In this example, we start with a string containing the number 10. We can explicitly convert this string into an integer using int as a function, and when we print it, we get the integer 10. Similarly, we can use float as a function to convert the string into a float. To go the other way around, we start with the integer 123 and explicitly convert it to a string using the str function. We can also take a decimal number and convert it to an integer. This conversion drops the decimal part, similar to the math function floor. Errors refer to unexpected behaviors or issues in your code. Errors can either prevent code from running or occur while the code is running. Understanding and handling errors is crucial for debugging and ensuring your code works as expected. There are three main types of errors in programming. First, syntax errors occur when there's a mistake in the structure of your code, preventing it from running. Next, runtime errors happen while the program is running, often due to invalid operations. like dividing by 0. Finally, logical errors don't cause the program to crash, but they lead to incorrect results, making your program behave in unexpected ways. Syntax errors happen when the Python interpreter encounters code that doesn't follow the language's rules. These errors are caught before the code runs. For example, in this case, we're missing a closing parenthesis in the print function. The interpreter will detect this and raise an error before executing the program. Runtime errors occur while the program is running, often due to illegal operations or conditions that can't be satisfied. These errors happen when the program is already in execution. For instance, dividing by 0 raises a zero division error, as shown in the example, where attempting to divide 10 by 0 will cause the program to stop with an error message. Logical errors don't cause the program to crash, but they lead to incorrect results or behavior. These errors can be tricky to debug because the program runs without any obvious issues. We must be careful of these the most. Always pay full attention to the logic of your programs. Python allows you to handle errors gracefully using try and except blocks. This lets the program continue running even if an error occurs. In this example, we're trying to convert the user's input to an integer. If the user enters something that isn't a valid number, like a string, a value error will be raised, and the program will catch it in the except block, displaying a friendly error message instead of crashing. User input allows your program to take information from the user and use it in your code. In Python, this is done using the input function. This function prompts the user to enter data, which can then be processed or used within your program. The input function is a built-in Python function that prompts the user for input and returns the entered data as a string. You can use this function to capture information like a user's name, for example. By default, the input function returns data as a string. When expecting numerical values, you need to convert it to the desired type, such as integer or float. When dealing with user input, errors can occur if the user provides data that doesn't match the expected type. For example, if you ask for an age and the user enters text instead of a number, it will cause an error. To handle such situations, you can use a try except block. This will allow your program to catch the error and prompt the user with a friendly message, ensuring it doesn't crash. When asking for user input, make sure to provide clear and specific prompts. Instead of just asking for temperature, you can ask the user to enter the temperature in Celsius. Clear instructions guide the user and ensure the data you receive is as expected. Clean code is essentially code that's easy to read, understand, and maintain. But why is clean code so important? First, it makes the code easier to review and debug, which saves time in the long run. It also improves collaboration, allowing team members to work together more effectively. PEP 8 is the Python's official style guide. PEP 8 stands for Python Enhancement Proposal 8 and serves as the go-to guide for consistent and clean Python code. The goals of PEP 8 are simple but powerful. It's designed to improve readability across different projects and to establish a common standard, making Python code easier to understand and work with no matter who wrote it. PEP 8 also provides naming conventions to help make code more readable and intuitive. For variables and functions, it recommends using snake case. These names should be meaningful and clearly describe their purpose. For classes, PEP 8 suggests using camel case, keeping names concise yet descriptive. Following these conventions helps create consistent, readable code that's easier to work with. For indentation, it recommends using 4 spaces per level rather than tabs. This keeps the code looking consistent across different files and editors. Additionally, PEP 8 suggests using blank lines to separate functions and logical sections, making the code easier to scan and understand. Another important PEP 8 guideline is managing line length and wrapping. It recommends keeping each line under 79 characters. This keeps code easier to read and ensures it fits well in standard editors. PEP 8 also has guidelines for using whitespace to keep code visually clean. Around operators, add spaces for readability. Inside parentheses, avoid extra spaces. Using whitespace consistently makes the code easier on the eyes and helps avoid misinterpretations. When it comes to imports, it recommends importing one module per line, keeping things clear and organized. Imports should also be separated into 3 sections: standard libraries, third-party libraries, and finally, local module imports. This structured approach makes it easier to see dependencies at a glance and keeps the code organized and maintainable. When writing functions, PEP 8 emphasizes keeping them clear and descriptive. A key guideline here is the single responsibility principle. Each function should perform one specific task. This makes functions easier to test and reuse in different parts of the code. Additionally, function names should be descriptive, like calculate area or send email, so their purpose is immediately clear. Finally, try to avoid side effects. Functions should ideally only work with the data passed to them and return a result, without affecting other parts of the program unexpectedly. Refactoring is the practice of regularly reviewing and enhancing your code's structure. One key tip is to break down large functions into smaller, single-purpose functions. This makes your code more modular and easier to work with. Also, keep your code consistent by following PEP 8 guidelines, as it adds clarity and a professional touch. And remember, consistency is often more important than following every rule perfectly. Consistent, readable code is the ultimate goal. Modular design is the practice of breaking down code into smaller, self-contained parts. Each module, whether it's a function, class, or file, serves a specific purpose, making the code more organized. A key principle to designing effective functions is the single responsibility principle, meaning each function should have one clear job. This keeps functions focused and easier to understand. Also, give your functions descriptive names like fetch user data or process transaction, so their purpose is obvious. Finally, try to keep functions short and simple. Aim for about 5 to 15 lines. If your function starts getting longer than that, it might be time to split it into smaller, more manageable pieces. A module is simply a single Python file that can contain functions, classes, or variables. You can import modules into other files to reuse code, making your projects more efficient. The main benefits of using modules are that they make large projects more manageable and promote code reuse and separation of concerns, helping you keep different parts of your project organized and independent. As an example structure for organizing your code into modules, you might have a main file for the core program logic, a utils file for helper functions, and a models file for data models or classes. This separation helps keep each file focused on a specific part of the project, making your code more organized and easier to maintain. A package is essentially a folder that contains multiple modules, and it's organized with a special init file with double underscores around. Packages are ideal for larger projects with many files. Packages allow you to group related modules by logical sections, making your project structure cleaner and more maintainable. Here's an example project structure using packages. In this example, you have a project folder with a main file, which handles the core logic. Inside the data processing folder, you have an init file to mark it as a package, along with 2 modules, cleaning and transformation, which handles specific tasks related to data processing. Of course, in a real project we would have other modules as well, but I omitted that for simplicity. It's important to document your code because it improves readability for others and for your future self while clarifying the purpose and functionality of your code. There's a difference between docstrings and comments. Docstrings are formal documentation used for modules, classes, and functions, providing clear descriptions of their purpose and usage. On the other hand, comments are informal explanations within the code used to clarify specific lines or sections as needed. A docstring is a string literal placed at the start of a module, class, or function, and it provides information about the purpose and usage of that code block. To write a docstring, you use triple quotes at the start of the block. There are several benefits for using docstrings. First, they allow users to understand what a function, class, or module does without needing to read through the entire code. They also support automatic documentation generation, which can be a huge time saver. Finally, docstrings improve the usability and maintainability of your code by providing clear, accessible descriptions of your code's purpose and functionality. PEP 257 provides guidelines for writing docstrings. According to these guidelines, start with a short summary of what the function, class, or module does. Make sure to capitalize the first letter and end the summary with a period. For consistency, always use double quotes. If necessary, you can add a more detailed description after the summary to explain the code further. When it comes to docstrings, there are two types: single line and multi-line. For simple functions or classes, you can use a single line docstring. It fits on one line and includes just a brief summary. For more complex functions or classes, a multi-line docstring is more appropriate. A multi-line docstring includes a summary line, followed by a blank line, and then a more detailed explanation if needed to clarify the functionality. Google-style docstrings is a widely used format for writing docstrings in Python. This style is popular because it's clear, organized, and highly readable, making it easier for both developers and teams to understand and maintain code. Many companies and developers prefer Google-style docstrings specifically for their readability and ease of use, as they present information in a logical, structured way. Each docstring usually starts with a brief description of what the function, class, or module does. Then, if the function has parameters, they're listed in an args section, where each argument is explained in detail. Next is the returns section, where you describe what the function outputs. Optionally, you can include a raises section to outline any exceptions the function might throw. This structured format makes docstrings informative and easy to follow. Here's an example of a Google-style docstring for a simple function that adds two numbers. This structure makes it easy for anyone reading the code to quickly understand the function's purpose, inputs, and outputs. When writing the args section of a Google-style docstring, use it to list the parameters that your function accepts. For each parameter, you should include the parameter name, its type, and a brief description of what the parameter represents. As an example, imagine we have a function that takes a person's name and age. Name is defined as a string representing the person's name, while age is defined as an integer for their age. This format makes each parameter's purpose and type immediately clear. When writing the returns section, use it to describe what the function returns. Start with the type of the return value, followed by a brief description. For example, if the function returns a greeting message, you'd write str to indicate the type, and then add a short description. Use the raises section to list any exceptions your function might throw, helping users understand what errors they may need to handle. For example, if the function could raise a value error when given invalid input, you would specify that. Docstrings aren't just for functions and classes. They can also be added at the beginning of modules to describe the module's purpose. For example, in a file for a car-related module, the docstring might start with a simple description like car module. Below that, you could include more detail to help anyone using the module understand its purpose right from the start. When a function returns a complex data structure, like a dictionary or a list, it's important to describe the structure in the return section of the docstring. For example, if a function retrieves student data and returns a dictionary, you can list the dictionary's contents in the returns section, specifying each key and its corresponding type. This level of detail makes the returned data easy to work with. To generate documentation for your Python code, you can use the built-in PyDoc module. First, make sure your script contains docstrings. Then, simply run the PyDoc command in the terminal. This will generate an HTML file with the documentation extracted from your docstrings. Keep in mind, though, that PyDoc has some limitations. It offers basic formatting and doesn't support custom styling. It doesn't support Google-style docstrings either, so it's more suited for quick default documentation. For more advanced documentation, you can use Sphinx, a popular tool for generating HTML or PDF documentation from your Python code. Sphinx supports Google-style docstrings, making it a great choice for maintaining clean, consistent documentation. It also offers advanced features like search functionality, customizable themes, and code highlighting, which can greatly enhance the user experience and usability of your docs. To get started with Sphinx, first install it using the install command. Once it's installed, initialize your project by running the quick start command, which will guide you through setting up the necessary files and directories. After that, configure your project by editing the config file to customize settings like the project name, version, and any extensions you want to use. To integrate Google-style docstrings with Sphinx, you'll need to install the Napoleon extension, which enables support for Google-style formatting. After installation, simply add Napoleon to the extensions list in your config file. Once that's done, run the make command to generate your HTML documentation, and Sphinx will process your Google-style docstrings properly. For better styling of your Sphinx documentation, you can add a theme. Popular themes include the RTD theme and Alabaster, among others. To install a theme, use the install command. After installation, simply activate the theme by updating the HTML theme setting in your config file. The config file in Sphinx is where you control your project settings. It's located in the main Sphinx project directory and holds various configuration options. Some common settings include the project name and author, extensions like Google-style docstring support, and the theme selection for your documentation. Here is a simple example of how the beginning of a config file could look like. Also note that Sphinx defaults to UTF-8 encoding, but you can specify the language of your documentation if needed by adjusting the language setting in the file. To add Google-style support in Sphinx, you need to include the Napoleon extension to the extension list like this. To control the appearance of your generated HTML documentation, you can select a theme. One popular theme is the RTD, which is the theme used by Read the Docs. This will give your documentation a clean, professional look. You can make other customizations in the config file. For example, you can set a custom title, add custom CSS or static files, or even add a logo and favicon. Once you've made all the necessary changes in your config file, make sure to save it. Then, to build your documentation, run the make command in the terminal. This will generate the HTML version of your documentation. You can find the generated files in the build HTML folder. To get started with Sphinx, the first step is to navigate to your project directory. If you're working in a terminal, type CD followed by the path to your project folder. On Windows, if you're using PyCharm, open the terminal within the IDE and you'll already be in the right project directory. Now, run the Sphinx Quick Start command followed by docs. This will create a new docs directory in your project to organize all your documentation files and initialize Sphinx. You'll be prompted with a few setup options. Choose Yes when asked if you'd like to separate the source and build directories. Then enter your project name when prompted and feel free to add details like the author and release version, or you can leave those blank if preferred. Next, configure the config file in Sphinx. To do this, open the config file which is inside the docs source folder. In this file, you'll see a list named extensions. Ensure that this list includes the extensions you need. At least we'll need Autodoc and Napoleon to support Google-style docstrings. To ensure Sphinx can locate your project files, add the root directory of your project to the system path. Put this code at the very top of your config file. Next, let's generate RST files automatically for each Python file in your project. Start by navigating to the docs folder and then run this command from inside the docs folder. This command instructs Sphinx to look in your project's root directory for Python files and create RST files for them in the source folder. Once you run this command, you should see RST files for each module in your project, along with a main file named modules.rst. Now let's update index.rst to include your project modules. Open your index file and make sure it looks like this. Finally, it's time to build the HTML documentation. In the docs directory, run the make command. On Windows, if you're using PyCharm, you might need to use the second version, which is slightly different. Either way, this command compiles your documentation and places the HTML files in the build HTML folder. To view the documentation, open index.html file in a browser. You should now see the main page with links to each module in your project. First, I'll go to File and select Settings. Under the Appearance section, I'll adjust the zoom to 125% so everything is easier to see. Next, still in Settings, I'll navigate to the Editor section and select Font. Here, I'll increase the font size to 17 for better readability. Now to create the project, I'll go to File and select New Project. I'll name the project Fitness Tracker, keep the default settings and click Create. I'll select Don't Ask Again, then choose this window to open the project in the current PyCharm window. If a pop-up appears regarding Windows Defender configuration, select Automatically to allow PyCharm to add an exception for the project folder in Windows Defender. Windows may also ask for permission, so be sure to allow it when prompted. To create the first file for our project, I'll right-click on the project's root folder, go to New, and select Python file. I'll name the file Fitness Tracker and press Enter to create it. For now, we'll start by creating a basic main function. Next, I'll create our second file and name it Exercise. In the exercise file, the main component will be our exercise data dictionary, which will store all the data we'll be working with. We'll also have a function to display a summary of the exercise data and another function to log exercise information. Finally, we'll create one more file and name it Input Validation. In this file, we'll have three helper functions. First, a function to get a non-empty string from the user as input. Next, a function to get a positive integer. And finally, one to get a non-negative integer. We'll handle the errors inside these functions, which makes the process of taking user input more convenient. In the Fitness Tracker file, right above the main function, I'll define one more helper function called AskForChoice. In the AskForChoice function, I'll use the getPositiveInteger function to prompt the user for a choice from a list of options we'll provide. Note that I press Tab on my keyboard to use PyCharm's autocomplete feature, which also automatically imports the helper function from the input validation module. Now make sure to return the choice from this function. Before asking for the user's choice, we'll print a welcome message and list the available options. In the main function, we'll add a while loop that runs indefinitely. Inside the loop, we'll use the ask for choice function to prompt the user for their choice. Then we'll add a simple sequence of if and elif statements to handle the cases we care about. Choice 1 corresponds to logging an exercise, so I'll call the log exercise function within its if statement block. The second option is show summary, but since I previously named it display summary, let's update it for consistency. Then we can call it in its elif statement block. Make sure to update the import to include the display summary function as well. For the last choice, we can simply print a goodbye message and use break to exit the while loop. That completes the main file for the most part. In the input validation module, we'll add a prompt parameter to each of the helper functions. In the first helper function, we'll prompt the user for input using the provided prompt text, then strip any extra spaces around the resulting string. At this point, if there's any value, we'll return it to the caller. This will terminate the function early, preventing it from executing the remaining instructions. However, if the value is empty, the return statement won't run, and the function will continue. To handle this, we can wrap the entire process in an infinite while loop, placing the error message immediately after the if block. Now that one line is longer than the available window space, I'll maximize PyCharm to give us a better view of the code. This completes the getNonEmptyString function. It prompts the user with our message, strips the provided string, and checks if it's not empty. If the input is valid, it returns the value. If not, it displays an error message and prompts the user again. In the getPositiveInteger function, we'll prompt the user for input and attempt to convert it to an integer. To handle cases where the user enters a non-integer value, we'll use a try-except block to catch any value error exceptions. I'll make sure to end each error message with a period for consistency. In this function, I'll also check if the value is positive. If it isn't, I'll display an additional error message. Once again, I'll wrap this in an infinite while loop. This function follows the same pattern as the previous one, using an early return in combination with the infinite loop to keep prompting the user until they provide valid input. For the last function, I'll simply copy this entire block and paste it there. The only change we need to make is to the if statement. Here, we'll also allow the value to be 0. In the fitness tracker file, where we're calling getPositiveInteger, we just need to update it to include a prompt. In log exercise, we'll first prompt the user for the exercise name, then ask for the duration and the amount of calories burned. Then, if the exercise doesn't exist in the dictionary yet, we'll add it. To handle that, we'll create a new helper function called insertExercise. I'll define it up here, but I won't implement it just yet. After inserting the exercise, if needed, we'll update its details with the duration and calories entered by the user. For that, I'll create one more helper function called updateExercise. This kind of separation of concerns keeps each function short and easy to understand. The last thing for log exercise is to print a confirmation message, letting the user know that the exercise has been logged. In insertExercise, we simply set the dictionary entry with empty values. Since we already check if the exercise exists before calling this function, there's no need to check again here. UpdateExercise is also very simple. We just need to add the minutes and calories to their respective entries in the dictionary. Again, there's no need to check if the exercise exists, as we've already handled that in the log exercise function. For show summary, we'll first print all the exercise entries. Then, to calculate the total duration and total calories, we'll add one more helper function for that. I'll name it Calculate Totals. It will simply sum everything up and return a tuple with both the total duration and total calories. To comply with PEP 8 style guidelines, let's break any lines that exceed 79 characters. Make sure to include parentheses when breaking up import statements into multiple lines, as required by Python's syntax rules. I believe I've already ensured that all other lines are 79 characters or fewer. We're ready to test the program now, so let's go ahead and do that. Make sure the fitness tracker file is selected, then click the play button. That will run the program and open this console window here. We can interact with the program by entering the requested values each time. I'll test it quickly with a few random values to make sure everything is working. You should experiment with it on your own for a bit to get a feel for everything that's happening. Even if you were able to follow along so far, it doesn't mean you fully understand what each part of the code is doing. Play around with the program as it is right now until you really understand how it all works. Then, dive into the source code, modify each part, and test the program again to see how those changes affect the execution. Don't be afraid to break anything. In fact, try to break it in every way you can think of. You can always return to the video to see how it was set up if you forget. Only this kind of tinkering will help you fully understand the program. If you're up for it, try recreating the project again from memory on your own. It's a great way to solidify your understanding, and don't be discouraged if you have to peek now and then to remember something you forgot. That's how we learn. You need to try, fail, and repeat. I've added Google-style docstrings for everything in the project, and I've also included these project files as resources in the course assets. Make sure to download them now. I don't mean for you to manually write all of these docstrings. This is a perfect use for text generation AIs like ChatGPT. Of course, just make sure to go through everything and confirm that it all makes sense in relation to the code you wrote. The point of documenting the code extensively like this is twofold. First, to ensure that future you and others can quickly understand what the code is supposed to do in a human-readable format, and second, for automatic documentation generation, which is incredibly useful. And for the latter, we first need to install the Sphinx plugin in our Python environment. To do that in PyCharm, I'll go to File and select Settings. Then under Project, I'll select Python Interpreter. I'll click on the plus icon to install a new package. I'll search for Sphinx, select it, and click Install Package. Then I'll wait until the installation is finished. Then I can click Close and OK. I'll wait until PyCharm finishes doing its thing. To generate documentation automatically for our project using Sphinx, the first step is to ensure that we are inside the virtual environment in our terminal. To check this, we can look at the path here. If it doesn't start with V&V, we'll need to activate the virtual environment manually. On Windows, we use this command to activate the virtual environment. Notice how we have V&V before the path. This indicates that we are now inside the virtual environment. Now that we're inside the virtual environment, I can confirm that Sphinx is installed by running the Sphinx build command with the -- version flag. Remember, we installed Sphinx in our project in an earlier lesson. Now, I'll initialize Sphinx inside a docs folder to keep our project organized. I prefer to separate the Sphinx source from the build files, so I'll choose Yes for that. Then, I'll enter the project name, my name, and a release version, just to make sure we don't leave them empty. PyCharm might take a moment to update the file directory. We can see that a docs folder has been created with several files in it. Let's open the config file. In here, we can see the information we entered during the Sphinx Quick Start, along with a bunch of other settings. First, I'll make sure to include Autodoc and Napoleon in the extensions list, since they are both required for automatic docs generation for Google-style doc strings. After that, I'll add the root folder of my project to the path to ensure that Sphinx can access all the source files it needs in order to generate the docs automatically. That's it for the config file for now. In the terminal, I'll first move inside the docs directory. From there, I'll run the Sphinx API doc command to automatically generate documentation files for all the Python files in my project. When we do that, Sphinx generates RST files for each Python file in our project. These are the documentation files essentially. Sphinx creates a modules file with links to each module in our project. However, I couldn't find a way to make Sphinx automatically include a link to the modules page in the index page, so we'll need to add that manually. First, I'll delete this paragraph, which just explains how to edit the documentation. Then, I'll add the word modules here. That's all we need to do. This ensures that Sphinx includes a link to the modules page in our documentation's index page. Now I can run the make command to finally build the documentation. Then I can navigate to the build folder and then to the HTML folder to view my documentation files. I'll right-click on the HTML folder, select Open In, and choose Explorer. Inside the HTML folder, I'll right-click on the index file, select Open With, and choose Microsoft Edge. And here's our documentation. It's quite simple, using the default theme, and doesn't have much content since our project is pretty small. However, it still functions as complete documentation, and it's nice to see the code presented in this human-readable format. I've created a new project called Dice Game for the second project in our course. Go ahead and create the same so you can follow along. I'll start by creating a file named Input Validation, which will be identical to the one from the last project. Next, I'll create a main file and add a placeholder entry point for now. Then, I'll add 4 more files to the project: Dice Game, Dice, Game Logic, and Display. In the Dice Game file, the core part of this project is the game state dictionary. First, we have the winning score constant, which represents the number of points a player needs to reach in order to win the game. Next, the init game state function returns the game state dictionary, which is the main data structure holding all the data for this project. This function takes the player names as arguments since it needs to store them in the game state. It also stores the scores for both players and keeps track of which player is about to take their turn. In the display module, we'll first add a display scores function. It will take the game state as an argument so it can access the players' names and scores. It does just that, then prints the players' names and scores in a nicely formatted way. Still in the display module, we'll add 2 more functions. Announce winner will take the game state as an argument so it can determine the current player and their name. Then, it will print a congratulatory message for that player for winning the game. Then, the display turn score function will just take a turn score as an argument and display a nice message with it. In the game logic module, we'll first have the get player choice function, which asks the current player whether they want to hold or roll again. We use the same pattern of having the input inside an infinite loop, so we can validate it and prompt the user to input again if it's not valid. In this case, we only have 2 valid choices, H and R. So we use the in keyword to check if the user's input is in the array containing our only 2 options. If it is, we'll return the choice. If not, we'll print a message and prompt the user to try again. In the game logic module, we're adding another helper function called player holds. I like this approach because it makes the code more self-explanatory. This function will call the getPlayerChoice function for us and check the result to determine if the player chooses to hold. This allows us to use the function as if we're asking a question. Does the player hold? It takes care of prompting the user for their choice and verifying their response. In the dice module, I'll add two functions. The first, roll dice, will simply return two random integers between 1 and 6, simulating the roll of two dice. I'll right-click on Random, then select Show Context Actions and choose Import this name. I can pick either of these, but I'll choose the second one. That simply makes PyCharm import the random module for me. I could have typed it out myself, and it wouldn't have made any difference. The Roll and Display Dice is a helper function that rolls the dice and displays a message with the rolled values. It helps keep the code more organized overall. First, it takes the current player, then uses the roll dice function to get the two rolled values. It prints a message with the current player's name and the rolled values. Finally, it returns the values to whoever calls the function. We're going to add one more function to the dice module, called isDouble. This function checks if the values of the two dice are the same, and if so, it prints a message warning that a double was rolled. It will also return true if doubles were rolled, or false if they weren't. This allows us to use the function as if we're asking a question, while it automatically handles printing the message for us. In the Game Logic module, we're going to add one of the key functions of this project, called playTurn. This function handles an entire turn for a player. It takes the game state as usual and uses a few functions from other modules. So let's import those. I trust you know how this works by now. I'm just using PyCharm to automatically add the import lines at the top of the code. I'll manually add isDouble since I'm already here. This is one of many reasons why using a modern IDE like PyCharm is so useful. Anyway, this function starts by setting a turn score local variable, which will keep track of how many points the current player will earn during this turn. The rest of the function is wrapped in an infinite while loop, meaning it will repeat indefinitely. The loop will stop when the player decides to hold, as we return from the function in that case. The actual turn consists of rolling the dice first. If the player is unlucky enough to roll doubles, the turn ends early with 0 points. That's the penalty for rolling doubles in this game. If that doesn't happen, the turn continues. The rolled values are added to the turn score, and the player decides whether to hold and end the turn with the current score or try their luck again. In the dice game module, we'll have another function that handles the turn at a higher level, called executeTurn. This separation is helpful because it allows us to treat a turn as a whole. We can call playTurn here and get the points it returns, then add that to the player's score stored in the game state. I need to include playTurn, since it's from another module and displays scores as well. In this section, we'll dive into the basics of object-oriented programming, or OOP, a programming paradigm focused on using objects to design and build software. Object-oriented programming centers around a few key concepts. First, we have classes, which define the structure of an object, attributes, the data or properties of an object, methods, which are functions belonging to an object, and objects themselves, which are specific instances of classes. Then there's inheritance, where one class can inherit attributes and methods from another, encapsulation, which is the principle of bundling data with the methods that operate on it, and polymorphism, allowing methods to be used in different ways across different classes. In object-oriented programming, a class acts as a blueprint for creating objects. It defines the attributes, or data, and methods, or functions that objects created from that class will share. Classes play a key role in organizing code by bringing together data and behavior. This approach encapsulates related information and functionality, making our code easier to manage, reuse, and understand. In Python, you create a class using the class keyword, followed by the name of the class and a colon. The general structure looks like what you see here. This simple structure sets up a new class, where you'll add attributes and methods inside the class body. Class attributes are variables that belong to the class and represent the state or properties of an object. In Python, we typically define attributes within the init method, which is a special method known as the constructor. This method initializes a new instance of the class, setting up any attributes needed for the object. In the example, we define a car class with an init method that takes in the brand, model, and year as parameters. Using self, which is a reference to the current instance, we assign these values to self.brand, self.model, and self.year. Self allows each instance of the class to have its own unique set of attributes. Class methods are functions defined within a class that describe the behaviors of an object. They can access and modify the object's attributes, making them essential for defining how an object interacts and operates. In this example, the car class has a method called displayInfo. This method returns a formatted string containing the car's year, brand, and model. By accessing the object's attributes through self, class methods like displayInfo allow each instance to perform actions or provide specific information based on its unique attribute values. After defining a class, you can create instances, also known as objects, of that class. Each object represents a unique instance with its own set of attributes and state. We can access the object's attributes directly, like mycar.brand, or call its methods, such as mycar.displayInfo. Each instance of the class operates independently, making objects flexible and allowing us to represent different real-world items with ease. It's important to understand the difference between a class and an object. A class is the blueprint. It defines the properties and behaviors that all objects created from it will share. An object, on the other hand, is a specific instance of a class. When we create myCar as an instance of the car class, it represents a unique item built from the class blueprint, with its own set of values for each attribute. So, why should we use classes in our programming? First, organization. Classes help us keep our code organized by bundling related data and methods together. This structure makes it easier to manage and navigate our code base. Second, reusability. Once we define a class, we can create multiple objects from it. This promotes code reuse, allowing us to apply the same blueprint to create different instances without rewriting code. Finally, encapsulation. Classes encapsulate data and behavior, meaning we can hide implementation details and expose only what is necessary. This abstraction simplifies complex systems and allows us to focus on the interface rather than the underlying complexity. Inheritance is a powerful feature that allows a new class to inherit attributes and methods from an existing class. The new class is referred to as a subclass or derived class, while the existing class is known as a superclass or base class. This relationship means that the subclass can access and utilize the methods and attributes of the superclass. Let's explore the benefits of using inheritance in object-oriented programming. First, code reusability. Inheritance allows us to extend existing classes rather than rewriting code. This reduces redundancy and enhances maintainability, as we can leverage existing functionality in our new classes. Next, hierarchical classification. Inheritance helps us create a clear structure of related classes. This organization makes our code easier to navigate and understand, as it establishes relationships between different classes. Finally, method overriding. Subclasses can provide specific implementations for methods defined in the superclass. This capability allows us to introduce more specialized behavior while retaining the common interface provided by the superclass. Now, let's see how inheritance works in practice. First, we define a superclass, also known as a base class, which will serve as the parent class. In our example, we have an animal class. In this animal class, we initialize it with a name attribute and define a speak method that returns a generic sound. This establishes a foundation that other classes can build upon by inheriting from animal. Next, we define a subclass, or derived class, that inherits from our superclass. In this case, we create a dog class that inherits from the animal class. Here, the dog class is derived from animal, meaning it inherits all the attributes and methods from the animal class. Additionally, we override the speak method in the dog class to provide a specific implementation. Finally, we can create instances of the subclass, which will have access to both the attributes and methods of the superclass. The subclass instance not only retains the inherited behavior from the superclass, but can also have its own specialized implementations, enabling a rich and flexible design in our code. The super function allows you to call methods from a superclass within a subclass. This is especially useful in cases of multiple inheritance, as it ensures that the correct method is called, maintaining the integrity of the class hierarchy. It also enables you to extend the functionality of the superclass method. While multiple inheritance can be a powerful feature, it also introduces complexity and potential issues, one of the most notable being the diamond problem. This occurs when a class inherits from two classes that share a common ancestor, leading to ambiguity in method resolution. To manage this complexity, Python implements a system known as the Method Resolution Order, or MRO. The MRO defines the order in which base classes are searched when looking for a method. This helps ensure that the correct method is called, but it can still lead to confusion if not managed carefully. To mitigate complications arising from multiple inheritance, it's essential to keep your class hierarchy simple and well-structured. This practice not only reduces ambiguity, but also makes your code easier to read and maintain. Always weigh the benefits against the potential pitfalls when considering multiple inheritance in your designs. Encapsulation in object-oriented programming is all about bundling data and the methods that act on it within a single unit, usually a class. This structure restricts direct access to certain parts of an object, preventing accidental interference and misuse of its internal state. By using encapsulation, we protect the integrity of the object's data, control how it's accessed and modified, and create more modular and organized code. Encapsulation is a key principle that keeps our code both reliable and maintainable. Encapsulation in Python is primarily achieved through access modifiers, which control the visibility of class attributes and methods. These modifiers determine how accessible certain parts of a class are from outside the class itself. Python provides 3 levels of access: public, protected, and private. Each level serves a specific purpose in managing access to the class's internal components, helping us maintain control over how data is used and modified. Let's start with the public access modifier. In Python, public attributes and methods are accessible from outside the class, meaning any code that creates an instance of the class can directly interact with them. By default, all attributes and methods in Python are public unless specified otherwise. Here, both the name attribute and the greet method are public, allowing us to directly access and use them outside the person class. Public access is convenient, but may expose data that could benefit from protection, which is where other access levels come into play. Next is the protected access modifier. In Python, protected attributes and methods are marked by a single underscore at the beginning of the name, signaling that they're intended for internal use within the class and its subclasses. Although protected members can still be accessed from outside, This convention suggests they shouldn't be directly modified or used externally. Here, name is a protected attribute, meaning it's meant to be accessed only within the person class or its subclasses. This level of access control helps to keep certain data somewhat hidden, while still allowing flexibility in inheritance. The private access modifier is the most restrictive form of encapsulation in Python. Private attributes and methods are prefixed with a double underscore, making them inaccessible from outside the class, even if we try to reference them directly. This enforces a stronger barrier, ensuring that these members are used only within the class itself. In this code, name is a private attribute, and greet is a private method. These members are hidden from direct access outside the person class, providing strict control over how they're accessed and modified. This form of encapsulation is useful for protecting sensitive data and implementation details. Encapsulation enhances code security and organization by hiding an object's internal state, protecting it from unintended changes. It also provides controlled access through getter and setter methods, which allow rules to be enforced when data is modified. Encapsulation supports modularity, enabling internal changes to a class without affecting the rest of the program. This structure makes code easier to manage, understand, and maintain as the project evolves. Polymorphism in object-oriented programming allows objects of different classes to be treated as if they belong to a common superclass. The term itself means many forms, and that's exactly what polymorphism provides, a way for a single interface to work with different underlying types. This flexibility lets us call methods on various objects without needing to know their exact class, making our code more adaptable and easier to extend. Polymorphism is primarily achieved through two key concepts: method overriding and duck typing. Method overriding allows a subclass to provide its own implementation of a method that's already defined in its superclass. This enables the subclass to modify or extend the behavior inherited from the superclass, offering greater flexibility. On the other hand, duck typing determines an object's suitability based on the presence of certain methods and properties, rather than its actual type. If an object behaves like a particular type, meaning it has the required methods, it can be used as that type. This approach adds a level of dynamism to our code, allowing it to interact with a variety of object types seamlessly. Let's explore how polymorphism works, starting with method overriding. In this scenario, a subclass can redefine a method from its superclass. Here, both the dog and cat classes override the speak method defined in the animal class. When we call animal sound with different animal instances, it will invoke the appropriate speak method based on the actual object type, showcasing how polymorphism allows for flexible and dynamic method behavior. In Python, achieving polymorphism often doesn't require a common superclass. Instead, we can define functions that expect objects with specific methods. In this example, when we call takeoff with either a bird or an airplane, it will invoke the respective fly method. This demonstrates duck typing in action, allowing us to work with different object types as long as they provide the expected method. Polymorphism enhances code quality by providing flexibility, allowing you to introduce new classes without modifying existing code, and promoting code reusability through functions that can work with any object implementing a common interface. Additionally, it simplifies code by reducing complexity and eliminating repetitive type checking, leading to cleaner and more maintainable programs. Polymorphism and inheritance are both fundamental concepts in object-oriented programming, but they serve different purposes. Inheritance focuses on creating a new class based on an existing class, enabling code reuse and the extension of functionality. On the other hand, polymorphism allows us to use a common interface to interact with different types of objects, regardless of their specific class. This distinction highlights how inheritance establishes relationships between classes, while polymorphism enhances flexibility in how we work with those classes. Abstract classes are essentially blueprints. They're not meant to be instantiated directly. Instead, they provide a structure for other classes to build upon. In Python, we use the ABC module, which stands for Abstract Base Classes, to create these abstract classes and methods. Abstract methods are methods declared within an abstract class without any implementation. This means that any subclass inheriting from the abstract class is required to implement these methods. By using abstract classes and methods, we enforce a contract for our subclasses, ensuring they provide specific functionality. Now, to implement abstract classes and methods in Python, we first import ABC and abstract method from the ABC module. Then we define an abstract class called shape by inheriting from ABC. Inside shape, we declare an abstract method named area. Notice that it has no implementation. We just use pass. Next, we create a rectangle class that inherits from shape. In the rectangle class, we define an init method that takes width and height as parameters. Here's where we implement the abstract method. The area method calculates the area by multiplying width and height. Now, attempting to instantiate the shape class would raise an error since it's abstract. Instead, we create an instance of rectangle with dimensions 4 and 5, and when we call the area method, it returns 20. Next, let's discuss interfaces in Python. Although Python doesn't have a strict interface type like some other languages, we can use abstract classes with only abstract methods to achieve similar functionality. An interface defines a set of methods that a class must implement, but it doesn't dictate how these methods should be implemented. This flexibility is particularly useful in polymorphism. With this approach, any class that implements the interface can be used interchangeably, allowing for more modular and maintainable code. In essence, using abstract classes as interfaces helps us enforce a contract for our classes while maintaining the freedom to implement the details as needed. We also have composition, which is an alternative to inheritance. With composition, instead of relying on a superclass, we use other classes as components within a new class. This approach allows us to build more modular code. One of the key advantages of composition is that it can reduce the tight coupling that often comes with inheritance. By composing classes, we can mix and match functionality without being locked into a rigid class hierarchy. In summary, composition provides greater flexibility and maintainability in your code, making it a powerful tool in object-oriented design. In Python, magic methods, often referred to as dunder methods due to their double underscore naming convention, are methods that allow you to define how instances of your class interact with built-in Python functions and operators. For example, by implementing the add method, you can enable the use of the plus operator to add objects of your class together. Now let's talk about the init and del constructors in Python. We already saw the init method, which serves as the constructor for initializing new objects. But Python also provides a del method, which acts as a destructor. The del method is called when an object is about to be destroyed, allowing you to clean up resources or perform any necessary finalization before the object is deleted or goes out of scope. Decorators like property, class method, and static method enhance how methods behave within classes. First, we have property, which transforms a method into a read-only attribute, allowing you to access it like an attribute while still maintaining control over its implementation. Next, the class method decorator enables a method to access the class itself instead of a specific instance. This is useful for factory methods or when you need to operate at the class level. Lastly, static method defines a method that doesn't operate on an instance or the class directly. It's ideal for utility functions that are relevant to the class, but don't require access to instance or class-specific data. By using these decorators, you can make your classes more versatile and maintainable, while also providing clear intentions about how methods should be used. UML, short for Unified Modeling Language, helps us visualize and document system architecture effectively. Let's take a quick look at the 5 main types of UML diagrams. We'll explore each of these in depth later, but for now, let's just see what they are. Class diagrams, perhaps the most common type of UML diagram, define the static structure of a system. They specify classes, their attributes, methods, and the relationships between the system's classes. Use case diagrams are also commonly used to capture the functional requirements of a system from the user's perspective. They often appear in the early stages of a project to gather and communicate the requirements for each part of a system. Sequence diagrams, while less common, illustrate how objects interact in a specific scenario of a use case. They are particularly useful for detailing specific interactions. Activity diagrams, though less common than class or use case diagrams, effectively illustrate the flow of activities within a system, much like a flowchart. They're often used to detail workflows and business processes, making them particularly useful for understanding and documenting complex logic. Finally, we have state diagrams. They describe the states of an object and the transitions between those states, used sparingly in specific situations. Class diagrams represent the static structure of a system. They include classes, attributes, methods, and relationships. This helps visualize how different parts of the system interact and are related. Visibility is crucial in class diagrams. Public visibility, shown as a plus sign in simple representations or a green circle in graphical UML diagrams, indicates that the attribute or method can be accessed by any class. Private visibility restricts access to attributes and methods within the class itself. It's depicted as a minus sign or a red square. Finally, protected visibility restricts access to the class and its subclasses. Is depicted as a hash symbol or a yellow diamond shape. Attributes are depicted as hollow shapes, while methods are shown as filled shapes. Class diagrams also adhere to basic rules of relationships. Association is shown with a solid line and optional arrows to indicate direction. Inheritance is depicted with a solid line and a closed arrow pointing to the parent class. Composition uses a solid diamond at the end of the line. Aggregation is represented by a hollow diamond at the end of the line. Class diagrams also follow basic rules of multiplicity. One-to-one means each instance of a class is related to one instance of another class. One-to-many indicates one instance of a class is related to many instances of another class. And finally, many-to-many means many instances of a class are related to many instances of another class. In class diagrams, relationships are depicted as follows. Association represents a relationship between classes. Inheritance denotes a parent-child relationship. Composition represents a whole-part relationship with dependence. Finally, aggregation shows a whole-part relationship with independence. Now let's talk about associations. Multiplicity is the term we use to describe how many instances of one class relate to another. One-to-one is pretty straightforward. One instance of a class connects to one instance of another class. One-to-many means one instance of a class is linked to multiple instances of another class. Many-to-many shows that many instances of one class relate to many instances of another class. Finally, optional means that sometimes an instance of a class might relate to one instance of another class, but sometimes it might not. Roles are labels you see at the ends or sometimes in the middle of association lines. They explain the part each class plays in the relationship. Even if these labels aren't placed exactly at the end, they still help visualize relationships and roles clearly. Directionality shows how navigable an association is. Bidirectional means both classes know about each other. Unidirectional means one class knows about the other, but not vice versa. And reflexive means a class has a relationship with itself. An association class is an association that also has properties. It links two classes while having attributes and behaviors of its own, making it more detailed and specific. Inheritance represents an is-a relationship. It shows how one class, the subclass, inherits attributes and behaviors from another class, the superclass. This relationship is depicted by a solid line with a closed, unfilled arrow pointing from the subclass to the superclass. Aggregation shows a whole-part relationship between classes, where one class comprises one or more instances of another class. It's depicted with a line and a hollow diamond at the whole side. Aggregation means the part can exist independently of the whole, so parts, like employees, can continue to exist even if the whole, like a team, is no longer there. In composition, the parts are tightly bound to the whole. If the whole is destroyed, the parts are too. Think of a body and its organs. If the body dies, the organs can't function independently. In this diagram, the body is the whole, and the organs are the parts. If the body is gone, so are the organs. Use case diagrams describe the interactions between users and the system. The main components include actors, use cases, and relationships. Use case diagram actors represent external entities that interact with the system, such as users or other systems. They are depicted as stick figures. For this example, our actors are the librarian and the member. Use cases represent the functionalities or services the system provides. They are depicted as ovals. For this diagram, the use cases are add book, borrow book, and return book. Association is a line connecting actors to use cases, showing interactions. Include is a dotted arrow pointing from one use case to another, indicating mandatory inclusion. Extend is a dotted arrow pointing from one use case to another, indicating optional behavior. An association is a line or arrow connecting actors to use cases, illustrating interactions. Directionality in associations often shows who initiates or is primarily involved in the use case. In this case, the arrow indicates that the user is the one initiating the withdraw cash use case. The include relationship indicates that a use case utilizes the functionality of another use case. It is mandatory, meaning the included use case is always executed as part of the base use case. This relationship is represented by a dotted arrow labeled include, pointing from the base use case to the included use case. The extend relationship indicates that a use case adds optional behavior to another use case. This is optional, meaning the extending use case may or may not be executed depending on conditions. It is represented by a dotted arrow labeled extend, pointing from the extending use case to the base use case. Sequence diagrams depict the flow of messages between objects over time. Key components include lifelines, messages, activations, and combined fragments. Lifelines represent the participants interacting in a scenario. Each lifeline is shown as a vertical dashed line, beginning at the top with the participant's name. Messages show communication between lifelines in a series of interactions. Messages are depicted as arrows between lifelines and can represent various types of interactions. Synchronous messages are depicted with a solid line and a filled arrowhead. They represent a call to an operation that waits for a return before continuing, typically activating the receiving lifeline. A dashed line represents the response back to the sender after processing the message. Asynchronous messages are depicted with a solid line and an open arrowhead. They represent a call that doesn't wait for a response to continue, and they do not activate the receiving lifeline. Activations, depicted as narrow rectangles along a lifeline, represent the period an object is active or processing a message. They show the duration of the execution of an operation or a process in the sequence. In sequence diagrams, we also have some unique diagrams that are called combined fragments. Alt, or alternative, is like your if-else statements. It shows different paths the sequence can take based on conditions. Opt, or optional, is like an if statement without the else. It represents a sequence that might or might not happen. Loop, as you might guess, represents repetitive sequences. Par, or parallel, shows parallel processing, where multiple things happen simultaneously. Alt is your go-to for showing conditional branches, much like if-else statements in programming. You use it when you need to depict different flows based on conditions, with each branch being mutually exclusive. Opt shows an optional sequence, kind of like an if statement without an else. Use it when you need to depict behavior that may or may not happen. Loop is used to represent repetitive actions. Use it when you need to show actions that repeat based on a condition or a number of times. Finally, par represents parallel processing. Use it when you need to show actions happening simultaneously. Activity diagrams illustrate the workflow of a system. They include activities, decisions, synchronizations, and swim lanes to show how tasks progress and interact. Activities show how control and data flow within a system or process. They are similar to the steps in a flowchart, highlighting the dynamic parts of a system. Activities are shown as rounded rectangles and symbolize specific actions or tasks. Flows or edges represent transitions from one activity to another, depicted as arrows connecting activities, nodes, and decisions. The initial node, shown as a filled circle, marks the starting point of the process. The final node, depicted as a filled circle with an outer ring, or a circle with a cross inside, signifies the end of the process. A decision is represented by a diamond shape and shows branching based on conditions. A merge node, also a diamond shape, merges multiple paths back into a single path. Fork nodes are shown as thick horizontal or vertical bars. They split one flow into multiple concurrent flows. Join nodes, which look similar to fork nodes, combine multiple concurrent flows back into a single flow. A decision node is shown as a diamond shape. It represents a point where the flow can branch based on conditions. Conditions are labels on the outgoing flow edges that specify the criteria for determining which path is taken. Swim lanes in activity diagrams help organize activities by showing who or what is responsible for them. They clarify which participant or system is accountable for each part of the process. State diagrams describe the states and transitions of an object. The key components include states, transitions, events, and conditions, showing how an object moves from one state to another based on events and conditions. States represent the various conditions an object can be in during its life cycle. Each state is depicted as a rounded rectangle. Again, a state represents a condition or situation during an object's life, depicted as a rounded rectangle with the state name inside, and the initial state, shown as a filled black circle, marks the starting point of the state diagram. The final state marks the end of the state diagram and is shown as a filled circle with an outer ring. Transitions represent the movement from one state to another and are depicted as solid arrows. State diagram events are triggers that cause transitions between states. They are depicted as labeled arrows, showing the cause of a state change. Conditions are Boolean expressions that must be true for a transition to happen. They are shown in square brackets along the transition arrow. Welcome to the world of databases. Here we'll cover the fundamental concepts you need to know. Imagine a digital filing cabinet, organized, structured, and easy to search through. That's how we can think of a database. It stores and manages data electronically, ensuring everything is in its place and accessible. There are mainly two types of databases. Relational databases are databases that store data in tables with rows and columns, much like a spreadsheet. Some popular examples are PostgreSQL, MySQL, and SQLite. NoSQL databases, on the other hand, handle data in various formats such as documents, key values, or graphs. MongoDB, Redis, and Neo4j are well-known NoSQL databases. Think of tables as organized collections of related data. For instance, a users table might store user information like names, emails, and passwords. Tables are made up of rows, which represent single records, and columns, which are specific pieces of data for those records. Let's talk about numeric data types in relational databases. First up, int. This one's for integer values, so think whole numbers like 42 or 1001. Next, we have float. These handle floating point numbers, perfect for decimals such as 3.14 or 0.001. Lastly, decimal. This type is for fixed point numbers, offering precise decimal values often used in financial calculations, examples being 99.99 or 0.10. We can also store character and string types in relational databases. Char is for fixed-length character strings, so if you store hello as a char type, it always occupies the same amount of storage. Varchar, on the other hand, is for variable-length character strings. Storing hello world as a varchar means it only uses the necessary amount of storage, making it more space efficient. Then we have text. This type is used for storing large text data, like long paragraphs or entire documents. When handling date and time in relational databases, there are several types you might use. For instance, if you're storing just the date, there's a type for that. Similarly, there's a type for time values. When you need to combine both date and time, the date-time type comes in handy. For cases where you also need to account for time zones, a slightly different type is available. And finally, if you're only interested in the year, there's a specific type for that too. For binary data, you have options for fixed length and variable length. Fixed length binary data always uses the same amount of storage, regardless of its content. Variable length binary data, however, only uses the space it needs, making it more efficient in some cases. Boolean types are simpler, representing true or false values. Think of them as the digital version of a yes/no toggle. Enum, set, and UUID are some interesting data types. First, enum is like a menu of options for your data, allowing you to choose from a predefined set of values. Think of choices like small, medium, and large. Set, on the other hand, lets you store multiple values from a predefined list, offering flexibility in your data choices. Imagine it like choosing multiple toppings for your pizza from A, B, C, and D. Lastly, there's UUID, a Universal Unique Identifier. It's a special type of identifier designed to be unique across systems, looking something like what you see here. JSON is a versatile data type for storing structured data in a readable format. It's perfect for things like user profiles, where you might store details like name and age in one compact object. Geometry, on the other hand, is tailored for storing geometric data. Whether it's points, lines, or polygons, this type is essential for applications involving spatial data, such as mapping and geographic information systems. A table schema acts like the blueprint for a database table. It lays out the structure of the table, detailing the columns and their respective data types. Think of it as a detailed plan that tells you exactly what kind of data goes where in your database, ensuring everything is organized and accessible. A table schema has a few essential components. First, the table name. It's what you'll call your table. Then, we have columns, which are the fields or attributes of the table. Each column will store a specific type of data, like integer, varchar, or date. Finally, there are constraints, which are rules that apply to the data, such as primary key, not null, or unique. Let's walk through creating a simple table to store employee information. First, we need to define the table name. This name should be descriptive of the data it holds. For example, you might call it employees. Then, we define the columns. These columns represent the data attributes you want to store. For an employees table, I've included some common attributes as an example. After that, we must choose data types for each column. I've also done that as an example. Lastly, we can add constraints if we need them. These are rules to ensure your data stays accurate and reliable. In this example, I've set employee ID as the primary key and set the first and last names as not null. This is the complete table schema for our example. That's what we would use to create the employees table. Lastly, we can also modify a table schema to add or remove columns. Although that's not recommended usually, sometimes we might need it. SQL, or structured query language, is how we talk to relational databases. Let's keep it simple and clear. You can write commands like select first name from employees. In this command, the words select and from are keywords from SQL. Although they are not required to be capitalized, it is a very well-established convention to do so. SQL, or structured query language, has a few key syntax rules to keep in mind. Using semicolons is important. They signal the end of an SQL statement. In some database systems, it's mandatory to separate statements with a semicolon. Line breaks and white space don't matter to SQL, so you can use them freely to make your queries easier to read. It's totally valid and even recommended to format a query over multiple lines if that improves readability. When you're dealing with strings, you should enclose them in single quotes. This is unusual, as most programming languages allow double quotes for strings, so make sure to remember this detail. Column names and table names can be enclosed in double quotes, especially if they contain spaces or reserved words. Although it's best to avoid such names when possible, sometimes it's necessary. When working with SQL, comments are handy for making your code more understandable. For single-line comments, use 2 dashes at the start of the comment line. This is useful for short notes or explanations. For more detailed explanations or multi-line comments, we can use the standard /* notation. Finally, I recommend you use indentation to make statements easier to read. You can pick your own indentation style, but make sure to be consistent throughout each code base. Let's talk about CRUD. This term stands for create, read, update, and delete. Think of it as the cornerstone of database operations. Whenever you're interacting with a database, you're likely performing one of these 4 tasks. Creating adds new data to the database. Reading retrieves data from it. Updating modifies existing data, and deleting removes data. But, as you can see here, the specific SQL keywords for each CRUD operations are not the same as the CRUD names, unfortunately. The good news is that we'll use these so much that they will soon become second nature to you, so don't worry about memorizing it just yet. When you want to add new records to a database, use the insert into statement. You can see its basic syntax here. This command adds a new record to the specified table. For instance, if you're adding a new user to a users table, you'd specify the columns and the values that correspond to those columns. You can efficiently insert multiple rows into a table in one statement. Here's how we could insert 2 new records into an employees table. You can also insert data into a table by selecting from another table. This approach allows you to transfer data from one table to another seamlessly. It's efficient for migrating or copying data within your database system. You can leverage default values that are defined in the table schema. For instance, if our employees table has a default value for the age field, you can insert a record without specifying the age, and it will automatically use the default value. Some databases provide a nifty feature where you can return data immediately after insertion. This command inserts a new record into the employees table and immediately returns the employee ID of the new record. It's a handy way to get confirmation and use the new ID right away. You can also use subqueries to insert data based on conditions from another table. This command inserts records into the high salary employees table by selecting from the employees table only those employees with salaries greater than $50,000. It's a powerful way to filter and move data around within your database. When you want to fetch data from a database, you use the select statement. Think of it as asking the database to show you specific pieces of information. In this example, column 1 and column 2 are the particular columns you're interested in, and table name is where you're getting this data from. To fetch everything from a table, use the select star statement. The star wildcard here stands for all columns. When you want to fetch specific rows from a table based on certain conditions, you use the where clause. If you have a table called students and you want to find students who are older than 20, your query would look like what you see here. You can also sort the results using the order by clause. To sort students by age, we could use something like this query. Here ask means ascending order. If you want descending order, use desk. You can combine multiple conditions to refine your queries using the AND keyword. For instance, to find students who are older than 20 and have the last name Johnson, you'd use a query like we have here. You can also use aliases to shorten your column names if you want to. In this query, first name is returned as F name and last name as L name. This can be useful when working with complex or lengthy column names. Another useful keyword is distinct, which removes duplicate values from your result set, ensuring each value appears only once. When you use distinct, SQL scans the specified columns and eliminates duplicate rows from the result set. The update statement in SQL is used to modify existing records in a database table. Its basic syntax starts with update, followed by the table name where the record is stored. Next, we use set to define the specific columns and the new values we want to assign. Finally, the where clause specifies which rows should be updated based on a given condition. Without the where clause, all rows in the table would be updated, so be careful to use it when only certain records need changes. To demonstrate the update statement, let's look at the employees table we used earlier. Suppose we want to update a single record, Alice's salary. We use the update command with the table name employees, followed by set salary equals 55,000, specifying the new salary amount. To target Alice's record, we include a where clause to limit the update to the row where employee ID is 1. This ensures that only Alice's salary is modified, while the other records remain unchanged. You can update multiple columns at once with the update statement. For example, if we want to change both Alice's last name and her salary, we specify each column and the new value separated by a comma. The update statement can also modify multiple records at once. For instance, if we want to set a salary of 60,000 for all employees hired before 2019, we can use a query like we see here. By adding a where clause that checks if hire date is earlier than January 1st, 2019, all records meeting this condition will be updated. SQL also allows us to use subqueries within an update statement to set new values dynamically. For example, if we want to update Carol's salary based on the average salary from another table, we can use a subquery like this one. The delete statement in SQL is used to remove existing records from a table. Its basic syntax starts with delete from, followed by the table name. We then add a where clause to specify which rows we want to delete. The table name identifies the table we're working with, and the condition narrows down the rows to delete. Without a where clause, the delete statement would remove all records from the table, so it's essential to use it carefully when only specific rows need to be removed. To delete a single record, we use the delete statement with a specific condition. For example, if we want to remove Bob from the employees table, we write delete from employees and add a where clause to specify employee ID equals 2. This targets only Bob's record, ensuring that no other records are affected. The delete statement can also remove multiple records based on a condition. For instance, to delete all employees with a salary below 55,000, we can use a query like this one. To delete all records from a table, we can use the delete statement without a where clause. You can also use a subquery with the delete statement to specify which rows to delete. For example, If we want to delete all employees hired before the average hire date, we can use a query like this one. When using the delete statement, it's important to follow some safety tips to avoid accidental data loss. First, always use a where clause. Without it, the delete statement will remove all rows in the table. Then, you should also test your conditions with a select query before executing the delete. This helps ensure you're targeting the correct rows. Lastly, consider wrapping your delete operations in a transaction. This allows you to roll back changes if you make a mistake, providing an added layer of safety when modifying your data. When using select to retrieve data, we can make use of the join keyword. In SQL, there are multiple types of joins. Let's start with the inner join and full join. The inner join is used to return only the rows where there's a match between both tables. So in this inner join query, we will only include rows where common column values match between table 1 and table 2. On the other hand, the full join includes all rows from both tables, showing matches where they exist and filling in with null where they don't. This way, every row from both tables is represented, even if they don't match on the common column. Now let's look at left join and right join, which allow us to pull all rows from one table while including only matched rows from the other. With a left join, you get all rows from the left table and only the matched rows from the right table. Similarly, a right join does the reverse. It returns all rows from the right table and matched rows from the left. Aggregate functions help us summarize and analyze data efficiently. 3 commonly used functions are count, sum, and AVG. Count is used to count the number of rows in a column. Sum adds up all values in a numeric column, and AVG gives the average value of a numeric column. In addition to counting, summing, and averaging, SQL offers aggregate functions to identify the maximum and minimum values in a column. Both of these functions are useful for quickly identifying the range of values within your data. Next, we have group by and having, 2 SQL clauses that help organize and filter group data, especially when using aggregate functions. Group by groups rows that share the same values in specified columns, creating summary rows for each group. Having works like a filter for these groups, letting us specify conditions on grouped data. Unlike where, which filters individual rows, having filters entire groups after they're created. In SQL, a transaction is a sequence of one or more operations that are treated as a single unit of work. Transactions are essential for maintaining data integrity because they ensure that all operations within them are either fully completed or not applied at all. If every operation within the transaction is successful, the changes are committed to the database, making them permanent. But if any operation fails, we can roll back the transaction, undoing any changes to keep the data consistent. Transactions in SQL follow 4 essential ACID properties to guarantee data reliability and integrity. Atomicity ensures that all operations within a transaction are completed as a single unit. If even one operation fails, the transaction is aborted and no changes are applied. Consistency keeps the database in a stable state before and after the transaction, ensuring it meets all defined rules and constraints. Isolation makes sure that transactions running concurrently don't interfere with each other, preserving the integrity of each transaction's results. Finally, durability guarantees that once a transaction is committed, it is saved permanently, even in the case of a system failure. To manage transactions in SQL, we use a few basic commands: begin transaction, commit, and rollback. Begin transaction marks the start of a new transaction, grouping a set of operations together. Commit is used to finalize the transaction, making all changes permanent in the database. If something goes wrong, rollback can be used to undo all operations in the transaction, restoring the database to its previous state.